Section: Introduction. In this section, we have witnessed remarkable progress in language modeling and image understanding within the research community. This progress has been made possible by the availability of large image text datasets and significant computing power, leading to the development of highly effective large language models, LLMs, and vision foundation models. These models have become the standard for addressing language and image understanding tasks. As a result of these advancements, a new area of multimodal foundation models has emerged, combining language and image processing into a single model with enhanced capabilities. Multimodal Large Language Models, MLLMs, are at the forefront of this development, utilizing both image and text data to generate text output. Following the success of LLMs, MLLMs are now seen as the next frontier in foundation models. When it comes to transparency, existing MLLMs can be categorized as either closed models or open models. Closed models are available for use but lack detailed information about the data, model architecture, and training procedures. On the other hand, open models release model parameters along with comprehensive descriptions of the data, model, and training setups, enabling the research community to further develop upon them. However, most existing works, whether open or closed, provide limited insights into the processes involved in making algorithmic design choices, especially in multimodal pre-training. To advance research in this field, we believe it is crucial to distill principles and lessons on how to construct models that can outlast specific implementations. Therefore, in this paper, we document our process of building MLLMs and aim to derive design principles that can benefit the community. Our contributions include conducting ablations on a small scale to analyze model architecture decisions and pre-training data choices. Through this analysis, we have identified key trends. For instance, we have found that factors such as image resolution, visual encoder loss and capacity, and visual encoder pre-training data play significant roles in modeling. Surprisingly, the architectural decisions on how visual data is inputted into the LLM seem to have minimal impact. Additionally, we have experimented with three types of pre-training data: image caption, interleaved image text, and text-only data. Our findings indicate that interleaved and text-only training data are crucial for few-shot and text-only performance, while caption data is most important for zero-shot performance. These trends have been consistent even after supervised fine-tuning, SFT, across various evaluations. Furthermore, we have scaled up our model by utilizing larger LLMs and exploring mixture of experts, MO, models. This has resulted in a family of high-performing models that outperform many existing works. Our pre-trained model MM1 has demonstrated state-of-the-art performance on tasks such as captioning and visual question answering, VQA, in both few-shot settings and across multiple benchmarks. Overall, our research showcases the effectiveness of large-scale multimodal pre-training in developing competitive MLLMs with desirable properties like in-context predictions and strong few-shot learning capabilities. We believe that the insights we have presented will remain valuable as modeling components and data sources continue to evolve. Section Summary. In this section, we delve into the realm of multimodal large language models, MLLMs, that combine image and text data to produce text, following the success of large language models, LLMs, and vision foundation models. We explore the importance of model architecture decisions and pre-training data choices, highlighting the significance of image resolution, visual encoder loss, and pre-training data types in achieving superior performance, even after supervised fine-tuning, SFT, and scaling up to larger models. Our findings showcase that our MLLM model, MM1, outperforms existing benchmarks in tasks like captioning and visual question answering, demonstrating the effectiveness of our design principles in creating competitive models at scale. Section: Recipe for building MM1. In this section, we delve into the process of constructing high-performing MLLMs, which involves a lot of practical experimentation. While the overall design and training methods are well defined, the specific details can vary. Our goal is to share the specific changes we made to create an effective model. We focus on three main areas: architecture, data, and training procedure. To assess the performance of our model efficiently, we use a simplified setup for our experiments. We start with a smaller base model configuration and make incremental changes to different components, such as architectural modules or data sources. By evaluating the impact of each change, we gradually refine our model data setup before scaling it up in terms of both model complexity and training duration. Our base configuration for these experiments includes specific details like the type of image encoder, vision language connector, pre-training data, and language model. We evaluate the effectiveness of these design decisions using zero-shot and few-shot performance metrics on various visual question answering and captioning tasks. When analyzing the components that enable our model to process visual data, we focus on how to best pre-train a visual encoder and how to connect visual features with the language model. We experiment with different pre-training methods for the image encoder, considering factors like image resolution and pre-training objectives. We find that the choice of image encoder and its pre-training approach significantly impact the model's performance on downstream tasks. In our experiments, we observe that contrastive losses lead to strong semantic understanding of images, while reconstructive losses are beneficial for tasks requiring detailed image comprehension. We also explore the impact of factors like image resolution, model size, and training data composition on model performance. In terms of connecting visual representations to the language model, we investigate different approaches such as average pooling, attention pooling, and convolutional mapping. We find that the number of visual tokens and image resolution have the most significant impact on performance, while the specific type of connector has less influence. Overall, our experiments highlight the importance of carefully considering design decisions in building MLLMs, especially when it comes to processing visual data effectively. Section Summary. In this section, we delve into the process of building high-performing multimodal language models, MLLMs, through empirical exploration. We focus on three key areas: architecture, data, and training procedure, where we conduct ablations to optimize model performance. By analyzing components like image encoders and vision language connectors, we identify crucial factors such as image resolution and encoder pre-training objective that significantly impact the model's performance on tasks like VQA and captioning. Section: Pre-training data ablation. In this section, we discuss the importance of data in training effective models. We divide the training process into two stages: pre-training and fine-tuning. During pre-training, we use large-scale web data, while in fine-tuning, we focus on task-specific data. We specifically look at the pre-training stage and explain our data choices. There are two main types of data used for training: captioning data, which includes images with short text descriptions, and interleaved image text documents from the web. Captioning data has short, relevant text descriptions, while interleaved data has longer, less relevant text on average. We also include text-only data to maintain the model's language understanding abilities. We conducted experiments using different mixes of captioning and interleaved data. We found that captioning data improves zero-shot performance, while interleaved data is crucial for few-shot and text-only performance. Combining text-only data with captioning data enhances few-shot performance, as long text helps the model understand context better. However, combining text-only data with interleaved data slightly decreases performance. Carefully mixing image and text data is essential for achieving optimal multimodal performance while maintaining strong text performance. We also studied the impact of synthetic caption data, VCAP, on few-shot learning. Despite being of higher quality but smaller in quantity compared to other caption data, VCAP significantly boosts few-shot performance. Based on our experiments, we determined the final recipe for MM1 multimodal pre-training, including the model setup, data mix, and training details. We scaled up the model size and used a mixture of experts approach to enhance model capacity without sacrificing speed. Our pre-trained models outperform prior work on captioning and VQA tasks, especially in few-shot performance. Section Summary. In this section, we explore the importance of pre-training data ablation for training high-performing models. We focus on the significance of using captioning data, interleaved image text documents, and text-only data to enhance model performance in various tasks. By carefully mixing these data types, we optimize multimodal performance while maintaining strong text understanding capabilities, leading to improved zero-shot and few-shot performance in multimodal pre-training. Section: Supervised Fine-Tuning. In this section, we will explain the supervised fine-tuning (SFT) experiments we conducted on top of the pre-trained models discussed earlier. For the SFT data mixture, we gathered around 1 million SFT examples from various datasets, including instruction response pairs from GPT-4 and GPT-4v, academic vision language datasets, text-only SFT data, and more. These datasets were combined and randomly sampled during training. We kept both the image encoder and the LLM backbone unfrozen during SFT. To handle higher image resolutions, we used positional embedding interpolation and sub-image decomposition techniques. By adapting our model, we successfully fine-tuned it to support image resolutions ranging from 65 by 65 to 67 by 67. We also compared our results with state-of-the-art models and explored the performance of MO models. We observed the impact of image resolution on model performance and the importance of pre-training on the final model performance. Additionally, we discussed the few-shot capabilities of our model and how pre-training influences SFT. Our findings suggest that pre-training with caption-only data enhances SFT metrics, and different VL connector architectures have minimal impact on the results. For a more detailed analysis, including qualitative examples and ablation results, please refer to the full paper.